good people of thermodynamics. My name is Ari, and I'm here with Gilad.
Hello.
He is British, and we're about to run through a Rankine cycle example. This is a very important Rankine cycle example. Professor Sherratt mentioned it's one of his favorites, and you can expect to see it on the final. So you should probably pay attention. So just to briefly explain what Rankine cycles are. What happens is you put heat in and you get work out. That's the idea of any power generating cycle. So when looking at a Rankine cycle, you can see here, there's a nice process diagram here. So what happens at state 1, you move and you go through a pump, and then increases the pressure a bit, and then you're at state 2, you go through a boiler, a boiler, and heat is added, Q in, and shoots up the temperature of the water up to a superheated vapor. What happens with that is this vapor is then pushed through a turbine, spins a shaft, and you get work out. After that, the temperature is decreased significantly through the turbine, and then it goes through a condenser. Through a condenser, the heat is rejected, bringing it back to state 1. And it's very important that you reject this heat because of first law, and you cannot beat first law. Isn't that right, Gilad?
Trust me, we've tried.
We tried beating first law, it just didn't work out. Anyways, as you can see on this process diagram, a Rankine cycle is made up of 2 isobaric processes. Sorry, those were not isobaric processes. What is that? All right, sorry to confuse. You have 2 isobaric processes. Notice these are the isobaric lines. And you have 2 isentropic processes. Those are those 2 lines because it's constant, because it's a TS diagram and it's constant entropy. Okay, so now we have this problem here, and the lovely Gilad is going to bring you through the calculations.
All right, so I'm going to bring you through the calculations from state 1 all the way to state 4, the fun stuff. All right, so let's go and look through this problem. So, a steam power plant, which is shown in this lovely diagram to the left, right here, operates a simple Rankine cycle. Steam enters the turbine, right here, at 3 megapascals and 350 degrees Celsius, and is condensed to a pressure, and is condensed at a pressure of 75 kilopascals. That's right here. All right, and we're going to eventually find out the thermal efficiency. But we're going to forget about the problem, and we're just going to go and focus on fixing the state at every point, from 1 all the way to 4. How do we do that? I'll show you now. So we'll start at state 1, because state 1 is the first one. At state 1, we can see on the diagram, it is on the line that's 75 kilopascals. See, right there, 75, works out. So P is equal to 75 kilopascals. And since state 1 is also on the saturation curve, we know that it is a saturated liquid. Meaning, the quantity is equal to 0. With this information, we can then go into the into our property books and find everything we need, which is going to be the specific volume, the enthalpy, and lastly, the entropy. Now, if you look into your table values, my personal property book does not have 75 kilopascals, which means that we're going to have to interpolate. So, in order to interpolate, we find the points before and the points after below and above 75 kilopascals. So, at 70 kilopascals, let's just do that. We have the specific volume to be 1.036 times 10 to the negative third. This is meters cubed per kilogram. The enthalpy is 376.7. This is kilojoules per kilogram. The entropy is 1.1919, and this is kilojoules per kilogram times Kelvin. At 75, we're going to find all these values at 75, but we're going to put it down just for us to see. And then at 80 kilopascals, we have the specific volume to be 1.038 times 10 to the negative third. The enthalpy to be 391.66, and the entropy to be 1.2329. So we're going to quickly solve for the enthalpy because I like doing that. And we're going to interpolate using the equation. So enthalpy at 75 kilopascals, which is our unknown, minus the enthalpy at 70 kilopascals over the enthalpy at 80 kilopascals minus the enthalpy at 70 kilopascals. This is all going to equal to 75 kilopascals minus 70 kilopascals over 80 kilopascals minus 70 kilopascals. So an easy way that I like to remember it is the number you're looking for minus the low number over the high number minus the low number. And it works on the same size. The number you're looking for minus the low number over the high number minus the low number. Now we just input all our values. So H at 75 kilopascals minus 376.7 over 391.66 minus 376.7 equals 75 minus 70 over 80 minus 70. We solve H 75 kilopascals to equal to 384.18 kilojoules per kilogram. Now you're going to do the same process for specific volume and entropy, but I'm going to leave you to that. We have the formula right here. You can change H to be S, or you can change H to be V, and it'll work for every situation. I'm just going to give you the values so that we can move on. So specific volume is going to be 1.037 times 10 to the negative third, and then entropy is 1.2124. Great, we now have all the values for state 1, and we can move on to state 2. Alright, so now let's move on to state 2. I love changing colors, so I'm just going to do different colors. Alright, so at state 2, we know that the pressure is 3 megapascals. That's right here. State 2 is on the isobaric line for 3 megapascals. So that's our pressure at 2. V equals 3 megapascals. Now, looking back at our diagram, we can see that from point 1 to point 2 is a straight line up, meaning that there is no change in entropy. It is an isentropic process. That means that S at state 1 is equal to S at state 2. Wonderful. Now, also knowing that both of these are to the left of the saturated curve line, these are both liquids. And so as a result, we know that we can assume that V, the specific volume at state 1, is equal to the specific volume at state 2. And since they're both liquids, we can then assume that it is the same as the specific volume for saturated liquid. With this information, we can now move on to the next problem. So, we can then use the formula, work done by the pump, which is negative because it's work being done to a substance, not the work being done from a substance, is going to equal to the saturated volume of the liquid times the pressure at state 2 minus the pressure at state 1. Since the specific volume is the same for state 2 and state 1, we can then continue using this number right there that we calculated earlier. So, let's plug in all the numbers. 1.037 times 10 to the negative third meters cubed per kilogram times 300 kilopascals, that's 3 megapascals converted to kilopascals, times minus 75 kilopascals, the pressure at 1. And now we have to convert all these units to kilojoules. So 1 kilojoule is equal to 1 kilopascal times meter cubed. This might seem like a redundant conversion because it's a 1-to-1 ratio, but in non-SI units we find that these conversions aren't always as simple. Now we solve for it. So that gives us 3.03 kilojoules per kilogram. This can be done in a calculator, very simply. Now we're going to go back to the first law, which is Q minus W equals delta H plus V squared over 2 plus gravity times the height. This is, as you can see, this is enthalpy. This is kinetic energy. And here is potential energy. And of course, the heat and work. These are both going in and out of the system. So, in this situation, we know since it's isentropic, there is no heat going into or out of this. So it's going to be 0. Q is going to be 0. We know that there's no kinetic energy because we're not specifically working on a mass flow rate. So that's also going to be 0. And the potential energy is also going to be 0 because we're not changing our height. So finally we're left with work is equal to delta H. Now we use this for our situation. So negative work pump is going to equal to H2 minus H1. So plug in all the values we have, 3.03 is going to equal to H2 minus 384.18. This was calculated above right here. Finally, you solve for H2, and you get 387.21 kilojoules per kilogram. And that is, you've now fixed the state. You fixed the state at state 2, and you can now move on to state 3. State 3 we know that the pressure is going to equal to the pressure at 2 because they're both in the same line. You see right here, this line right here, and it's a 3 megapascal line. So that's going to be 3 megapascals. We are also given the temperature at state 3 in the problem, 350 degrees Celsius. So we have the pressure, we have the temperature. So all we have to do is look in our property tables and find the enthalpy and entropy. So enthalpy is going to equal to 3115 kilojoules per kilogram. And the entropy is going to equal to 6.74 kilojoules per kilogram times Kelvin. State 3 is done. That was the easiest and fastest steps we have done. Now we can move on to state 4. So at state 4, and this is now going to be the trickiest of states, we know that the pressure is equal to the pressure at state 1. We're also given that pressure. That pressure is 75 kilopascals. Remember from before. We also know that since from state 3 to state 4, it's a straight line down. It is isentropic, which means S3 equals S4. S3 equals S4, which equals to 6.74 kilojoules per kilogram times Kelvin. Wonderful. Now we look through our property tables, and we see that at pressure 75 kilopascals, and since it's within in the saturated curve line, we know that it is a mixed substance, which means it's both solid and it's both liquid and gas. So when we look through our property tables, we find that it falls right in between the entropies that are present at 70 kilopascals and 80 kilopascals from the saturated liquid all the way to saturated vapor. So we know that it is a mixed substance. So what we have to do now is find the quality. So we start with the equation S4 equals, so the entropy at state 4 equals the entropy of a saturated liquid plus the quality times the difference between the saturated of a liquid and the entropy of a saturated liquid and the entropy of a saturated gas. We can then move this around and find out the quality at state 4 is equal to S4, entropy at 4, minus entropy of a saturated liquid over the difference of a saturated liquid, the entropy of a saturated liquid, and the saturated gas. We have all these lovely figures, so we can then just plug it straight in. That's going to equal to 6.74 minus 1.2124. This can be interpolated uh, from your property book, or you can use the same numbers that we found up above right here. It's these values right there. And that's going to be over the difference between the entropy of the saturated liquid and the saturated gas, which happens to be 0.245. That value is going to have to be interpolated, and you have to calculate it yourself just by subtracting the entropy of a saturated gas and the entropy of a saturated liquid. This equals 0.886.
Okay, Ari's back. And so working from this, you can see that the quality is about 88.6%, right? And normally, actually, in the real world situations, you wouldn't want a quality so low. You would want something more along the lines of 95%. Because what happens is that this, when the water vapor mixture is this quality, it's actually running through the turbine. And so what that means is that there are these little droplets of water that are flying at super fast speeds through this turbine, and what will actually happen is they have so much force to them they'll actually break the turbine and shear off the blades. So you don't want that, but for the sake of this problem, we're just going to run with it. Okay. So now what we're doing is we're going to take this quality and we're going to find H. So we're looking for H4. So now what you do is you're going to find HF plus X HFG. So you can find HF and HFG from your property table. And so we'll just put them right into that equation and find HF based on this mixture. So we're going to find H4 based on this mixture. So it's going to equal 384.18 plus 0.886 times 2278. So altogether, H4 is going to equal 2,403 kilojoules per kilogram. Okay, consider your states fixed. Congratulations. Now, the problem was asking, what is the thermal efficiency? Now, when we evaluate engineering processes, you always want to find out the efficiency to know, if you're actually designing a good system and using good pressure, temperature, all the factors. So, thermal efficiency, we know the thermal efficiency equation to be the work net divided by Q in. And so when we're looking at the at the process curve, here you have your saturation curve, our process looks something like this, right? Actually goes below the line and across. So you have state 1, 2, 3, and 4. So looking at the equation for thermal efficiency, which is the work net divided by the Q in, if we want to look at that graphically, the net work is the entire area inside the process curve, right? And then the work net, and then the Q in is going to be the area underneath the top line, so the line where the heat is being transferred into the system. So that's what it looks like. But okay, we can equate the thermal efficiency to be 1 minus Q out over Q in. What that means is basically the efficiency of the entire system is the work that you're rejecting from the system over the work that you're bringing into the system, and you subtract that from 1. Pretty simple. Okay, so we want to find a number for Q out, and we want to find a number for Q in. Luckily, we have all of these numbers that we calculated, so we can pick the ones that we need for this. Okay, we know from first law that Q minus W, as said above, is delta H plus kinetic energy plus potential energy. okay? And we know in all these cases, kinetic and potential energy can be neglected. Now, what we're looking at here is the Q out. Okay, we're going to look for the Q out term. And what that is this area underneath this bottom curve. So going from state 4 to state 1, right? And we know that there's no work happening between state 4 and state 1. The only work that's happening is with the pump, and the other work that's happening is with the turbine over here. So we can say that the work goes to 0 for this portion of the graph. Okay, so now we want to find Q out, which is this area under here. Now we know that when heat is expelled from a system, it's negative heat, right? So what we're going to say is that Q out, because we want to find a value for this, is going to be negative delta H, so we could say that it's H4 minus H1. So it's the enthalpy at point 4 minus the enthalpy at point 1. Great. Now, you're going to say, where do I get these values? Well, congratulations, you fixed all these states. They're right above you. So we know that H4 is 2,403 kilojoules per kilogram. And H1, if we scroll on up, is right here, which is 384.18. 384.18 kilojoules per kilogram. So now, Q out, we can do the very simple math, is 2,019 kilojoules per kilogram. Okay? Now we want to find Q in, which is positive, so we do not have to flip anything around. And that's going to also be delta H because, again, there's no work happening on this curve. So Q in is going to equal H3 minus H1. The enthalpy right here minus the enthalpy, sorry, not H1, H2. Sorry to confuse. So it's the enthalpy at point 3 minus the enthalpy at point 2. Then I'll give you your Q in. So we plug in some values, which again we calculated above, which is 3,115 minus 387.21. And we can do the simple math and find that Q in equals 2,728 kilojoules per kilogram. Great. So now it seems like we have all of our values. Now we take our thermal efficiency, we say it's 1 minus Q out over Q in. That equals 1 minus 2,019 divided by 2,728. If we run those numbers, we're going to find that the thermal efficiency to be 0.26. So in percentage terms, that's about 26%. Great. Now we have our thermal efficiency, and you solved the problem. You can see here that efficiency is 26%, and in reality, in practical terms, 26% actually isn't that great for a Rankine cycle. And there are a lot of measures you can take to improve this, which you will or have learned about. Okay, thank you so much. That was the Rankine cycle problem from me and Gilad. I hope you enjoyed and learned something. Could be anything, but something. Have a good night.